Mastering deep learning. CNNs reign supreme in image processing, manipulating data with convolutional and pooling layers. Why do convolutional neural networks, CNNs, which are a type of deep learning algorithm that are particularly effective in image and signal processing, play a crucial role in various applications such as image classification, object detection, and image segmentation, and how do they utilize the concept of convolutional and pooling layers to obtain increasingly complex and abstract representations of the input data? Convolutional neural networks, CNNs, are a type of deep learning algorithm that have revolutionized the field of image and signal processing. They have demonstrated unparalleled success in various applications such as image classification, object detection, and image segmentation. The key to their success lies in their ability to extract increasingly complex and abstract representations of the input data through the use of convolutional and pooling layers. At the heart of a CNN lies the convolutional layer, which is responsible for extracting local features from the input data. This is achieved through the process of convolution, where a small window of weights, known as a filter, slides over the input data, computing the dot product at each position to generate a feature map. This process is repeated with multiple filters, resulting in a set of feature maps that represent different aspects of the input data. The feature maps generated by the convolutional layer are then passed through an activation function, such as the rectified linear unit, ReLU, or the hyperbolic tangent, TANH, to introduce nonlinearity into the model. This allows the CNN to learn and represent more complex relationships between the input data. However, the convolutional layer alone is not sufficient to extract complex and abstract representations of the input data. This is where the pooling layer comes into play. The pooling layer, also known as downsampling, reduces the spatial dimensions of the feature maps, thereby reducing the number of parameters and the number of computations required in the network. This has several benefits, including reducing the risk of overfitting and improving the robustness of the model to small transformations in the input data. There are two main types of pooling layers, max pooling and average pooling. Max pooling selects the maximum value from each window, while average pooling takes the average value from each window. Both types of pooling layers reduce the spatial dimensions of the feature maps, but max pooling is more commonly used due to its ability to retain the most important features. The combination of convolutional and pooling layers is the key to the success of CNNs. By stacking multiple convolutional and pooling layers, the network is able to extract increasingly complex and abstract representations of the input data. The output from one layer becomes the input to the next layer, allowing the network to learn hierarchical representations of the input data. In the context of image classification, CNNs have achieved state-of-the-art performance on various benchmark datasets such as ImageNet. The CNN is able to learn hierarchical representations of the input images, starting from simple edges and lines, to more complex objects and eventually the entire image. In object detection, CNNs have been used to locate objects within images and classify them simultaneously. This is achieved through the use of region proposal networks, RPNs, which generate proposals for object locations, followed by a CNN to classify the proposals. Finally, in image segmentation, CNNs have been used to assign a class label to each pixel in the image. This is achieved through the use of fully convolutional networks, FCNs, which remove the fully connected layers and use convolutional layers to output a class label for each pixel. In conclusion, the ability of CNNs to extract increasingly complex and abstract representations of the input data through the use of convolutional and pooling layers has led to their widespread adoption in various applications such as image classification, object detection, and image segmentation. Their ability to learn hierarchical representations of the input data has enabled them to achieve state-of-the-art performance in many benchmark datasets.